Welcome to our next chapter, Chapter 5 in our environmental chemistry course called Water for Life. We consider water and really never lost its mystery. After at least 2.5 millennia of philosophical and scientific inquiry, the most vital of the world's substances remains surrounded by deep uncertainties. Without too much poetic license, we can reduce these questions to a single bare essential. What exactly is water? And that is a quote directly from Philip Ball in his text Life's Matrix. So things that we'll consider in this particular chapter: do you know where your drinking water comes from? Do you know if your drinking water is safe to drink? And how do you know? These are very essential questions, and as our story begins with our water chapter, we talk about the unique properties of water. Clearly, water is essential to our lives. All living organisms are composed of water. Living, it is a liquid at room temperature, what is actually very incredibly unusual for such a low molar mass. What do we mean by that? Hydrogen and oxygen. We know that off the periodic table, oxygen and hydrogen, when added together, give us a molar mass as follows. We have 1 as the atomic weight of hydrogen plus another hydrogen plus the atomic weight of oxygen gives us a sum of 18 grams per mole. The molar mass of water, 18. It's a very low number. Now, other molecules with also low molar masses are not liquids at room temperature, they're gases. For instance, nitrogen, molecular form of nitrogen, with each one contributing 14, it has a molar mass of 28 grams per mole. And diatomic oxygen, of course, is 16 and 16, which is 32 grams per mole. And carbon dioxide, what we exhale and contributing to greenhouse gases, has a molar mass of 44 grams per mole. Carbon weighing 12, and each of the oxygen contributing 16, 12 plus 16 plus 16 gave me a molar mass of 44. So what we're saying is water has this very unusual property that it's actually a liquid at room temperature, but other molecules with similar molar masses are all gases at room temperature. So what that might mean, well, the water molecule itself, we'll investigate, has very unique properties based on the strong intermolecular attraction based on its geometry. It takes an incredible amount of energy to get water to boil. So 100 degrees Celsius, and water is also unusual is that it is the only liquid that actually expands when freezes. So any other substance, as you take thermal energy away, those molecules slow down, and as you slow down, they begin to contract. But water actually expands, and it does so by creating these hexagonal shapes. You can envision a snowflake, if you will, and as they begin to organize into these hexagonal shapes, they actually will expand when freezing. Have you ever left a bottle in the freezer and had it expand to where it might have even exploded? We can see these different representations of water. We've talked about water being a polar molecule, and we're going to revisit what does it mean to be polar in terms of just the molecular shape and also in terms of the bonds themselves. We'll introduce this word again called electronegativity, how electronegative is an element, its ability to attract electrons in a shared pair. So if we practiced in previous lessons writing out the water molecule in terms of a Lewis dot structure, we know oxygen, who lives in group 6A, has 6 valence electrons, and we would represent those with 6 dots around its symbol. Hydrogen, who lives in group 1A with its 1 valence electron, fills in those bonding sites, giving us 2 single covalent bonds. But now we also understand that based on molecular geometry and what we call the valence shell electron pair repulsion theory, water is not a linear molecule, but instead we called it bent. The molecular shape of water is bent. It has 2 bonded pairs, but 2 unbonded pairs of electrons, and we wanted to give all of the room possible. So think about all of this room up here available for the electrons to spread out and stay as far apart from one another as we can. So we'll discuss the term polar in terms of electronegativity. When we have a shared pair of electrons, not all atoms share them equally. We have a unit known as electronegativity, and we define that term as an atom's ability or attraction for electrons in a shared pair in a covalent bond. The greater the difference in electronegativity between the two bonded atoms, the more polar the bond. Let's take a look at what we have here. Fluorine is the most electronegative element. That means that fluorine, who's the smallest nonmetal on our periodic table, has the ability to really attract electrons in a shared pair. So if I were considering a molecule such as hydrogen fluoride, those are two dots, a little molecule here with a single bond. Notice that hydrogen has an electronegativity value of 2.1, and fluorine has an electronegativity value of 4.0. When I take the difference between 4 and 2.1, I find 1.9. So the electronegativity difference is 1.9. So that obviously shows that we have a polar molecule. Now the word polar means this single bond here between the H and the F, even though the shared pair is between the two atoms, we really have a significant pull towards the fluorine, creating a large electron density around the fluorine, and we show that by showing a little negative partial charge. And over on this side, the hydrogen, of course, who is also sharing the electrons, but the density is being pulled away from it towards the fluorine, it's left with a partially positive charge. The more electronegative element, fluorine, is pulling the electron density towards its own nucleus, creating what we call a polar molecule, a molecule that has regions of positive and negative distributed throughout based on electron distribution. And we say that the bond is polar because they are not being equally shared. And we'll practice some of those concepts in greater depth. Fluorine is the strongest of strong, non-metal, the most electronegative element there is. The closer you are to fluorine, the more electronegative you are. So electronegativity actually increases as you go across the row towards fluorine, and it actually decreases as you go down a column because atoms are getting bigger and bigger. So the closer you are to fluorine, the smaller you are, the more electronegative you have. And so what we start to think about is in terms of electronegativity, like if we said between a single bond between carbon and oxygen, just as another example. Oxygen has an electronegativity value of 3.5. Carbon has an electronegativity value of 2.5. And if I subtract them, again, it doesn't matter which order, I just want the difference between them, the electronegativity value is 1.0. This is a more polar bond. See how the value is much larger? Although this is also polar. And I would show the polarity of the bond by pointing towards the more electronegative element. The bond is polar because the electron distribution is being pulled from the carbon towards the oxygen, making this a much more negative region, leaving the positive on the carbon. The molecule is polar and the bond is polar. So an electronegativity difference allows us to calculate if the bond is polar and degrees of which bond is more polar, considering several different examples. Sometimes, and we'll just say the electronegativity value greater than or equal to 2 is actually representing what we'll soon learn is an ionic bond. The only difference, if it's 0.0, we would call that a nonpolar bond. Absolutely no difference in electronegativity is a nonpolar bond. 0.0 electronegativity difference. So how might that occur? Well, if I had a fluorine to a fluorine, right? 4.0 minus 4.0, two identical atoms bonded together, gives me an electronegativity difference of 0. This is a non-polar bond. If I had something like chlorine, which is 3.0, with nitrogen 3.0, they're assigned the same value, so it would be considered a non-polar bond. So with that in mind, let's rank these elements according to their electronegativity. So either with the electronegativity value or just the periodic trend, we're going to be able to assign numbers. The closer you are to fluorine, the more electronegative you are. And so I saw fluorine with a value of 4.0. How about the potassium? Now potassium isn't even listed here. Notice that it's going down the first group, 1A. That periodic trend says H, then Li, then Na, and underneath that on our periodic table would be potassium. I would predict it to be smaller than 0.9, simply because the trend says as you go down a column, the numbers get smaller. And so even though it's not listed there, I know potassium is going to be smaller than 0.9. How about gallium, Ga? Now again, gallium didn't make the list, but where gallium is kind of in this area of the periodic table. So again, with the trend saying potassium in the same row as gallium, it's going to be a greater electronegativity value. Carbon and then cesium. Of course, this would have the lowest number. So the largest atom, cesium, and again, I just want to remind you, it goes hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. So this is the first column. Cesium is a much larger atom. It would have a smaller electronegativity than potassium, who would then have a smaller electronegativity than gallium, because we're moving across now on the periodic table. As we move across, they start to get a little bit bigger. Between carbon and then the strongest of strong, fluorine. So this is the most electronegative. Remember on our periodic table, if we just think about the trend, fluorine up by here, well, I guess I should make that a little clearer. My periodic table is pretty rough, isn't it? So general trend here, these are the columns, we'll say this would be helium. So right here is fluorine, and down here would be cesium in just the general direction. So electronegativity is the highest top right, it is the lowest bottom left. And the game simply becomes from the farthest away to fluorine, closest to fluorine, you can rank them based on their electronegativities. So this electronegativity difference determines the polarity of the bond. In a water molecule, we have a polarity that exists between, and I guess I should make this bent. It looks like a right angle. When I would think about the polarity of the hydrogen molecule here, I'll just stick here. We have the polarity being pulled towards the oxygen, the more electronegative element. So therefore we know that this is a polar bond. A polar bond is a covalent bond in which electrons are not shared equally, but rather displaced towards the more electronegative element. When we looked up oxygen's value of 3.5 on our electronegativity chart, compared that to hydrogen's 2.1 on the electronegativity chart, the difference was 1.4. As long as it's not 0, it's considered to be a polar bond. The only time it's non-polar is if it's exactly 0. The water molecule itself is polar, and because of the shape. Now remember these exposed electrons when we were drawing those Lewis dot structures? how the hydrogen to oxygen bond is polar, but the geometry of the entire molecule is also polar, just because there's this electron distribution of this negative cloud up here of electrons, making this region more negative and the hydrogens more positive. To remind ourselves what a polar substance is, it's the same structure that has an area that's positive and an area that's negative, just as a bar magnet does. If you've ever seen in your physics class, your physical science class, a bar magnet, it has stamped on it a positive end and a negative end, attractions of opposite charges. And so as we start to consider opposite charges, if I held another bar magnet close to this one, what it would be attracted to is the negative end of the other magnet. And this is an attraction that we're going to talk about in molecules as well. If I consider the attraction, this negative oxygen is going to be attracted to another hydrogen molecule, but it's going to be attracted to its positive area. And I can see an attraction between positive and negative, setting up intermolecular forces. So here we have a HH, the electronegativity value of two like elements would be 0, so it's said to be a nonpolar bond. And look at here, if I have electronegativity difference for ionic compounds, you're looking at about 1.9, 2.0, saying pretty much at that point, if the difference, typically you say if it's 2.0 or greater, they're not sharing anymore, they're actually transferring electrons, where sodium would develop a +1 charge and chloride would develop a -1 charge, and we called that an ionic bond, where we just look at the Lewis dots instead of, so there's 7 dots around this chlorine. And what we would do then is show the metals are losing electrons and the nonmetals gain electrons, forming ions. And we'll talk more about that in a future lesson here as well. So, is it polar or nonpolar? Let's take a look at these Lewis dot structures and decide, these are the structures and then they're drawn out for us. Are these molecules polar? I'm going to take this first one drawn, SO2, and even though it's written down here, I'm going to just draw it a little bit bigger from what I see. Notice on the central atom, there's a pair of electrons that are not bonded, and then I have some oxygens in either direction. The reason I'm drawing that bigger is this area is very critical because I have 1, 2, 3 electron domains, and we studied that when we talked about geometry, 3 domains around that central atom. 2 of the domains are bonded, both of them to the same element, oxygen, and 1 is unbonded. The lone pair of electrons here is the unbonded pair. This is kind of the test I always use for polarity. If I stand in the center atom and I have to look at all directions of electron domain, I look left, I look right, and I look up. The 3 directions for electron domain, are they all exactly the same? Then it would be nonpolar. Or are they different? Because of the 3 domains, 2 are bonded and 1 is not bonded, this makes it a polar molecule with the region of negative on those exposed electrons. This molecule is polar. There is not a symmetrical center atom. But now let's consider carbon dioxide, a very similar structure, but let's take a closer look at how it's different. So just redrawing. Notice here the carbon does not have any central electrons, any unbonded. So there's 2 domains. 2 are bonded, both to the same element, oxygen, and there are 0 unbonded. So of the 2 domains, am I looking at exactly the same thing? I only have 2 positions to look. Look left, look right. There is no up or down. Only 2 domains exist. They are identical. This is a nonpolar molecule. If I stand here at the carbon, we have carbon is the central atom. There's 4 domains. There's an up, down to hydrogen. There's a left, right to chlorine. Of the 4 domains, are they all identical? Well, 2 of them clearly are hydrogen, 2 of them are clearly to chlorine. They are not identical. Therefore, this is a polar molecule. I would see the electron distribution here on the chlorine not being equal to a hydrogen distribution. The electron density would be pulled towards the chlorine, the more electronegative element. And here on this central atom, phosphorus, there are 4 domains. 3 of the 4 domains are attached to chlorine, but there is a lone pair of electrons. Because it has a lone pair of electrons, it is a polar molecule. Let me see if I can clear that up. This is the same slide. I'm just cleaning it up here. So here's the sapling. Indicate the direction of polarity for each of these covalent bonds by dragging the appropriate delta notation. Is it partially negative or partially positive? And that brings us back to this little slide here. Just to remind us, the more electronegativity the element possesses, the closer it is to fluorine. And so all we're being asked to do here, who's closer to fluorine, carbon or oxygen? Well, oxygen it's more electronegative, and therefore I'm going to assign the partial positive sign to carbon and the partial negative sign to oxygen. Now this one's unusual. Oxygen to chlorine, they're both position 1 from the fluorine atom, but remember the smaller atom is more electronegative, so between oxygen to chlorine, oxygen is more electronegative, and so therefore it receives the partial negative and chlorine receives the partial positive. Now who's closer to fluorine, oxygen or fluorine? Well, of course fluorine. And so we'll see the trend, just assigning partial positive and partial negative. The closer it is to fluorine, the more negative, the stronger that pull is towards the nucleus. And so the process continues. Just to clarify what we're saying, if I were to just redraw that, the bond is polar, the electron distribution is being pulled more to the electronegative element, the higher value on our electronegativity chart. If you're unsure, just find them. Between chlorine and carbon, here's carbon at 2.5, here's chlorine at 3.0. And once I find those values, it's real simple to go ahead and put those in. So the partial negative goes to the more electronegative, partial positive to the carbon. For each of these molecules below, specify the polarity of the bonds and overall polarity of the molecule. So here we have a central atom, beryllium. Notice that it only has 2 domains. From beryllium to chlorine in either direction. There is no up or down, only 2 domains. So therefore, because there's only 2 domains and they're both identical, the molecule is nonpolar. But the bond itself would pull the electron density towards the more electronegative element between beryllium and chlorine. That is a polar bond. Chlorine is more electronegative. Here's a water molecule. We said water has 4 domains, so the molecule is polar. Not all 4 domains are exactly the same. I can look up, look down, and see electrons. Look left, look right, and see hydrogens. That's a not symmetrical central atom, so it's a polar molecule. And we can clearly see that the bonds are polar, knowing that you'd be pulling them towards the oxygen, the more electronegative element. So the bonds would be pulling this way. And here, of course, we have a diatomic molecule, so we'd have a nonpolar bond. Identical atoms bonded together would have an electronegativity difference of 0. And the molecule is nonpolar because it's evenly distributing its electrons around both of those oxygens. Which of the following substance has polar interactions between the molecules? So I think it just simply helps to kind of visualize. In that first example, we have a chlorine attached to a chlorine. Of course, this would have an electronegativity value of 0, so this would be a nonpolar molecule, and therefore no interactions occur. Now, nitrogen trifluoride, nitrogen has 5 valence electrons, so I'm going to start with 5 dots, and then I can see how the fluorines would attach to fill those electrons with its 7 valence electrons, and we'd end up forming single bonds around each of those. And I could continue in the same way. So we'd end up with 3 single bonds. Once I see that, there's 4 domains, but only 3 are bonded and 1 is not bonded. Because of this lone pair of electrons, the molecule is polar and therefore would have interactions. This is the region that would be partially negative with those exposed electrons. In a fluorine-fluorine, same as chlorine-chlorine, 2 identical atoms bonded together would not be polar, electronegativity difference of 0. And chlorine-fluorine, if you remember, it also has a value. The electronegativity difference is 0.5, so it would be a polar molecule. The electron distribution would point towards the fluorine ever so slightly, making this region a little bit more negative and this region a little bit more positive. So the 2 diatomics, chlorine and fluorine, are nonpolar, and the NF3 and ClF, the 2 molecules that we drew, are indeed polar. We can pause our lesson here. We've done a great job so far just introducing the special qualities of water, talking about polarity of the molecule. We'll pick up with our next lesson, the role of hydrogen bonding,